Hi, my name is Christina Tiutin, and today I am going to present our collaborative approach regarding test case prioritization based on neural networks classification. First, we will begin with an introduction where we discuss the motivation and the research methodology. Then we continue with the solution overview, where we look into the development of our approach. Furthermore, we will focus on experimental design and analysis. And lastly, we will conclude our results with a discussion of the future work. Let's begin with the introduction. Regression testing is an essential process that most of the software systems go through a various number of times. Its target focuses on validation of modified software, aiming to detect if new errors were added into previously tested code and to provide confidence that modifications are correct. However, the challenge which arises in regression testing is that test suites are prone to become so large that running all test cases would be time consuming. There exist many approaches dealing with this problem, ranging from test suite minimization to test case selection and test case prioritization. Test case prioritization, or shortly TCP, is a technique that tries to optimize which test cases should be executed first by setting them up in a certain order such that faults are detected as soon as possible. Test case prioritization methods undertake the costly execution time of regression testing by prioritizing test cases which are sufficient to test new changes and to detect faults early. A systematic literature review was conducted to indicate the state of the art and to outline the ongoing scientific research on TCP-related algorithms. The image describes the methodology behind this process with all the steps that we have followed in our research. There has been observed an interest towards machine learning-based approaches in TCP. The basic workflow starts with creating a set of training data comprising of various features of the test cases. Each test case is assigned a label corresponding to a class based on some criteria. A machine learning algorithm can then be trained on this dataset in order to classify new test cases. The general idea is that test cases predicted with highest priority disclose the most important faults early in the testing phase. Within the systematic literature review process, we have come across a number of papers which appear to relate to our focus. Out of this, we have selected two. The paper by my coordinating teacher proposes the TCP formalization that considers not only test requirements, but also functional requirements and dependencies between the functional requirements. A second proposal is a version-specific test case prioritization. A machine learning-based supervised approach is used here. An artificial neural network classifier is built and trained in order to assign priorities to new test cases. Our approach builds on top of the TCP formal definition from the first paper and uses the neural network classification approach from the second one, of course with some additional improvements. The contributions of this work are a proposal for test case classification used for test case prioritization based on various factors, including associations between requirements, tests, and discovered faults. An operationalization of our strategy using artificial neural networks to obtain the assigned execution priorities of new test cases. Experiments with models incorporating different features, architectures, and optimizers, and a set of experiments designed for both real and synthetic data to prove the efficiency of our approach regarding fault detection rate and prediction accuracy. Let's continue with the solution overview. The overall framework of our test case prioritization based on neural network classification approach consists of three phases: data preparation, training, and deployment or validation. The figure graphically depicts this process. Using the TCP formalization from the first paper and also the target vector defined in the second paper, we compose our feature collection. The feature vector uses the following metrics: number of modified requirements covered, number of dependent requirements covered, normalized cost, number of faults discovered, effectiveness, and efficiency of the test case. The value used for labeling is computed as effectiveness plus efficiency minus 1. Based on the obtained values, we have established three classes for test cases. In the first phase, we structured our approach rather as a replication study of the work from the second paper. We have implemented the multi-classification approach described there by following their steps. Creating a target vector with balanced distribution of samples by labeling test cases with values between 0 to 2, building a classifier with the reported architecture, and preprocessing the training sets by encoding classes into a binary class matrix, and also scaling and standardizing the input feature vectors. However, based on their structure, we have also created our own experiments. When building the model, there are several parameters that need to be taken into account. In this research, we have considered both stochastic gradient descent and Adam optimization algorithms. To summarize the proposal, we have the architecture model as described in the second paper, which is model 1 in the table. This one uses stochastic gradient descent optimizer and has the following structure: 2 hidden layers with each containing 20 nodes, an output layer with 3 units based on the 3 priority classes, and relative activation function used for hidden layers, while sigmoid function is used for the output layer. Afterwards, we have our proposals, which are model 2 to model 6 in the table. These are other neural network architectures with various layers, different numbers of hidden neurons, and they also used either stochastic gradient descent or Adam optimizer. Furthermore, we will look into the experimental design and analysis. Regarding the dataset, this case study draws data from the software artifact infrastructure repository that contains software used in various types of testing experiments. From the available software programs, grep object was chosen as real dataset, mainly because it met the prerequisite of having the test information in the required format. It consists of 470 test cases per test suite and also 70 requirements. Using the methodology of generating instance spaces for machine learning classification, we have constructed a new dataset, a synthetic one, starting from the grep object. We have augmented our initial dataset with 500 samples by using a Gaussian mixer model to generate instances with the desired target vector of features. Considering the experimental setup, the first figure outlines the various dimensions that we considered in the design of our experiments. Thus, we have the following: various architectures with 6 neural network models, various set of features, partial or all, where partial considers only the modified requirements covered and dependent requirements covered as metrics for the target vector. Dataset, real or synthetic based on the grep object, validation, holdout or k-fold. The conducted analysis of the proposed artificial neural network model is performed from 3 perspectives as outlined in the second figure. This is done using model performance matrix to analyze the neural network models, considering accuracy, precision, and recall, statistical tests to investigate the difference between the proposed models based on the Wilcoxon signed rank tests, and also average percentage of false detected metric, or shortly APFD, which is used to compare our neural network classification-based test case prioritization approach with a baseline, the retest all random approach. The results are displayed with respect to the previously mentioned perspective, which are performance metrics, statistical tests, and average percentage of false detected metric. Regarding the performance metrics, the initial experiments were conducted having first in mind 2 points of view: the partial versus all features of the target vector. However, we found the experiments for the all features to be more relevant, and thus we only displayed those results in our presentation. The accuracy, precision, and recall for the grep dataset using holdout validation method are provided in table 5. We can notice that models 2, 4, and 6 perform better in terms of accuracy, while model 2 performs the best in terms of precision, and models 2, 4, and 6 regarding the recall. Table 6 shows the accuracy, precision, and recall results for the synthetic dataset considering the holdout validation. Model 6 performs best in terms of accuracy, while the best precision is achieved for model 1, and for recall models 3, 5, and 6 reach the best results. Table 7 shows only the accuracy metric for the synthetic data set in the case of the k-fold validation for 2 folds. The best accuracy is achieved for model 6 in the second fold. Looking at these results, we can notice that the models which used Adam Optimizer obtained better results. For statistical tests, the Wilcoxon signed rank test was used to compare the proposed models, either varying the type of features used, the optimizer used, or the architecture of the neural network. The 4 tables present the p-values in different cases. First, table 8 compares the experiments with different types of features, partial versus all. In 3 cases, for models 2, 3, and 6, the values obtained are less than 0.05, meaning that we can reject the null hypothesis. And thus, there is a statistical difference between the models that use partial features and those who use all features. Then in table 9, we compare models which use different optimizers. The stochastic gradient descent optimizer versus the Adam optimizer. Table 10 shows the models which use the same optimizer, stochastic gradient descent, but different architecture models. Table 11 also shows the results of the tests applied between models with different architecture but the same optimizer, Adam. In these 3 cases, the results are performed with respect to the 2 data sets, real and web-based synthetic. And unfortunately, the values are not less than 0.05, and in these cases, we cannot draw any conclusion based on the results. Regarding the APFD metric, the approach was the following. We have generated a new synthetic data set. Then, based on this data set, we have generated a random permutation of the test cases. We computed the APFD metric for this permutation and obtained a value of 16%. Following, we have applied model 6 for the same generated data set. We have ordered the test cases according to the obtained classification and reached an APFD metric of 18%. Thus, we can say that our neural network classification-based test case prioritization approach obtained a better fault detection capability. And lastly, we close this presentation by drawing conclusions and mentioning the future work. Through this work, we propose an approach for test case prioritization by applying artificial neural networks. The association between requirements, tests, and discovered faults is included as part of the factors based on which the neural network is able to assign priorities to new test cases. The neural network models were validated using 2 data sets, a real one and a synthetic one, generated based on the real one using the Gaussian mixture model. The outcome of the result shows a better reliability for Adam optimizer and an artificial neural network with the 3-layered architecture. We have also conducted statistical tests to compare various proposed models from the first perspective, which include the neural network architecture, optimizer used, number of features, data set, and validation method. Future work will investigate the test case classification problem by combining other metrics as independent variables. We also plan to extend the experimental evaluation, considering other open source projects, in order to evaluate the efficiency of the suggested metrics for the target vector. Thank you very much for your attention. We are open now for discussions. Thank you.